think we can start. Good morning or good afternoon, depending on your geographical location. My name is CM Wang, and I'm the TMR Chair Professor in Structural Engineering in the School of Civil Engineering, University of Queensland, Australia. I would like to begin by acknowledging the traditional custodians of the land on which we meet today and pay my respects to the elders, past and present. I extend that respect to Aboriginal and Torres Strait Islander peoples here today. As today's webinar facilitator, it gives me great pleasure to welcome all of you to the Blue Economy CRC 4th webinar for this year 2021 on multi-purpose platform and co-location of aquaculture and wind farms, and especially to our very eminent speakers, Professor Frank Adam. He heads the engineering department of DECON, as well as he is a professor in Rostock University in Germany, and as well as Professor Maurizio Kulu from Strathclyde University, Scotland. Now, to ensure attendees can see both the presenter and their slides, please activate your screen on speaker view. Now, all attendees are encouraged to use the Q&A function during the webinar, and the speakers will answer any questions you have at the end of their presentations. Of course, limited to the time constraint, we may not be able to cover all questions, but we attempt to do so. So our first speaker is Professor Frank Adam, who leads the Wind and Energy Engineering Division at DECON. And the title of his presentation is Multi-Purpose Platform Design for Floating Offshore Wind and AC/DC Topsides. I now invite Frank to give his presentation. Frank, please.
Thank you, CM, for this introduction, and also thanks for the invitation to provide information about this project at this very interesting webinar session. Yes, as already mentioned, my presentation is about floating offshore wind operation maintenance topside / hub, and also the possibility to combine it with an AC/DC / transformer topside for offshore wind purposes. The motivation behind that project is quite simple. As all of you know, in Europe, we have a very strong offshore wind community, and especially in the past, already a lot of fixed offshore wind farms were installed. So the first wind farm, for example, was installed already in the early 90s. Since that time, a lot of other offshore wind farms were installed close to the coastline, far away from the coastline, in water depth up to round about 40, 50 meters. And when you're going far away from the coastline, there is an issue with regard to the operation and maintenance costs, especially to transfer the crews, the operation maintenance crews, from shore to the offshore location, to the offshore wind park. And especially this was the motivation to start thinking about an operation and maintenance platform, fixed platform, to have the crews similar to oil and gas platforms offshore over a certain time, let's say 2-3 weeks, and they are operating directly from this platform, and they are maintaining the offshore wind farm by living and working at the platform inside the offshore wind farm. And now the offshore wind community is at the edge to enter a new, let's say, decade, enter a new century, especially to going to floating offshore wind. So fixed was, let's say, more or less the past, and now the community is going into deep water, far away from the coastline. And what deep water means, and what is meant also with the potential offshore wind electricity you can get from offshore wind, is presented at this slide, especially in the picture on the left-hand corner. So you see that as the offshore wind potential in deep water far away from the coastline is significantly higher than close to shore in water depths up to round about 50, 60 meters. Meaning those offshore wind farms, those floating offshore wind farms need need an operation and maintenance in a way that it is cost competitive, that the costs are quite low, to keep the level size cost of the whole project, of the whole wind farm on a low level. And therefore an floating operation and maintenance solution is needed, also maybe in combination with fish cultures, etc., offshore, which can get the electricity from the offshore wind farm. And in addition, it's also needed to have floating transformer platforms available to convert and also to transfer the offshore power, the offshore electricity direct to shore, or convert the electricity to hydrogen and pass it via a pipeline or ships to shore or to other countries, other continents. We, as GCON, together with the University of Rostock, worked with a lot of other partners from the EU in a project by name Space at Sea, and parts of the results of this Space at Sea project will be highlighted during this webinar, during this presentation. For example, the highlight will be set on the so-called energy production, where an offshore wind park is used to provide electricity to an operation maintenance hub / to offshore production facilities. Other work packages within that project dealt with fish and algae cultivation offshore, or a so-called transport and logistic solution where floating substructures for floating harbors or logistic centers offshore were developed. And a nice example of wave tank tests can be seen here. It was the first tests which were performed at Maren in 2015 or 16. In between, additional tests were performed and can be seen also at the Space at Sea webpage and or under at the webpage from Maren. But today's highlight will be on this so-called energy production on the so-called operation maintenance hub based on the Space at Sea project. The project, this is from my understanding also very important to know, was not only done by GCON and the University of Rostock. There were a lot of partners. The partners and the consortia were led by Maren. We had big names in like DMGEOC, ICE, a marine design consulting service from Romania, and also the universities of Delft, Hamburg, Harburg, etc. So a very strong consortia to perform the work. And the project, this is maybe something I would like to highlight, ends last year in October. So all the results you can see during my presentation are from, let's say, from a finished project. Some impressions with regard to our work, some impressions with regard to the hub. So you can see here on the left-hand side, the operation and maintenance solution. It's a topside adapted from the, let's say, oil and gas business in a way that we worked together with the potential offshore users, requesting their needs, requesting their ideas, how to design such a topside in a way that is, let's say, user-friendly. Means they love to live there, they love to work there, etc. And an impression with regard to this outcome can be seen on the right-hand side, because most of the potential end users requested a nice view to the wind park during the working day so that they see where they are working. But in the evening, they would like to have something like a green garden to relax. And that's the reason why we have this internal here, this green garden solution in the inside of the topside. So meaning a lot of the space is used for the living purpose, for the relaxing purpose. Some key data with regard to this topside are summarized at this slide. So we are talking about a topside with a ground area of 32 times 32 meters and a height of 8 meters on 2 floors. In addition, and this is something which can be seen here, we designed the complete topside in a way that we are connecting the floors via beams and not with walls. So meaning the end user and the later operator is completely free to design the space, the area at the deck in a way he would like to have it later on for his employees and or for his purpose or her purpose. Especially these decks can be used later on also for a transformer station or an storaging station, whatever, if you bring in a battery package here or an electrolyzer, etc. So meaning this modular design was the basis for low cost, because you can see it here, the modules are designed in a way that we have in total 2 models, as you know it, for example, from container ship building industry. So the center model and the corner model, and all can be fabricated in a serial way, so that the costs are also low in comparison to specified and single solutions. Where we are now, so we ended at the Space at Sea project with the basic design. So we have done a complete FE analysis of the topside for the specific O&M purpose. So the complete and set of ultimate limit state loads were calculated to get in touch with the resistance of the topside and to design it in a way that we are working on the safe level, considering a bit also fatigue loading by increasing the loading from the ULS side in a specific way, so that this design can be seen as a front-end engineering design, especially on this level, to go forward with a detailed design phase in a later stage with a later project. Some nice pictures from these FE calculations can be seen here. So you can see again the decks and also the beams we used for the interconnection between the floors. And you see also the interface as columns to the substructure, to the floating substructure. So meaning this a universal interface, those columns here can be the interface to an TLP substructure, can be the interface to a semi-submersible substructure or a barge type substructure, as you want, as the operator would like to have it later on, or as the boundary conditions at sea based on the mid-ocean conditions are defined. This picture shows you the outcome of the strength analysis, only to show you that our calculations were, let's say, done. You see here for sure in the lower part of the beam the highest strengths. That is quite sure, because those beams are highly loaded because of the external loads. Some mass properties of the primary steel structure of the topside are summarized at this slide, whereas I would like to highlight this mass of around about 400 tons here is excluding any internals, excluding any equipment, etc., etc. So meaning for sure the mass need to be increased, or will definitely increase based on the usage for this topside later on. Some nice pictures also on the drawings. So you see here also this typical ship deck design with stiffeners and the plate on top. So more or less state-of-the-art technology combined with a new usage with for a new industry sector. Now I would like to present you some videos. Hopefully it works. This is an impression from the top side when you're going through the floor on the second deck into your working space. For example, here you're sitting in your working space, having a look outside to the offshore wind farm. On the next impression, in the next video, you see where people can do their daily workout after a working day. So you see here the fitness room at the second floor. And the third impression is you're going downstairs at the first to the first floor, and you have a nice view into the, let's say, green garden as part of this operation and maintenance hub. Okay, the summary slash also an outlook. So I presented you a multi-purpose platform for, at the moment, operation and maintenance, which can be adapted quite easily also for transformer and maybe also hydrogen platforms offshore. The design is a modular design to adapt it. Overall, this is also the next step. So the University of Rostock applied together with some partners from Europe to design and adapt this design for a so-called AC/DC transformer platform in combination with a hydrogen solution to produce hydrogen offshore and also to store it. Especially storaging can be done via the help of the gravity anchor here. And the outlook, this is something Mauricio, the second speaker in this background, knows very well. So Scotland has a lease round at the moment out there, and we are expecting a lot of floating option agreements in the near future, and all those floating offshore wind parks needs, or some of them needs for sure an operation and maintenance hub or a floating transformer station. And this is also our idea to go ahead with the results of a research project funded by the EU to bring it into the water later this decade. So hopefully in 2026 up to 2030. And the first discussions with potential end users are ongoing. And on a research point of view, as already highlighted, University of Rostock applied together with companies and also research institutions for funding to adapt the O&M topside for a hydrogen platform and transformer platform solution. And in addition, we are also working on a proposal for an interdisciplinary approach for a graduate school to educate PhD students in the field of offshore wind from an interdisciplinary point of view. So integrating knowledge from the social scientists with regard to acceptance questions, etc., but also providing them information in the field of all those technical topics like engineering on topsides, substructures, etc., to get well educated and PhDs afterwards, which have a wider view also for this multi-purpose platform solutions later in the future. Thanks. That's it from my side.
Thank you very much, Frank, for a very, very interesting talk. Congratulations on your project, which is so. I look at your internal space. It's so beautiful. It's almost like in a hotel. And
yes.
may I ask, what is the design wave height and significant wave period that you're looking at for your platform?
Yeah, so the site conditions which were chosen for the design during the project are from the North Sea. So we worked with a maximum wave height of around about 70-80 meters in the first stage. That's also the reason why we work with these columns. So meaning if we are going to other sites, we can shorten or increase the length of the columns to consider other conditions, let's say it in that way. For sure, also the topside need to be adapted. But in the end, this was the idea behind to work with these columns as an, let's say, interfacing component to adapt the solution quite easily for other sites.
And also, Frank, if I can ask, how much does it cost you, your entire platform, if you want to purchase?
Yeah, that's a very good question. So what we have done a cost benchmark against other solutions like a mothership approach, so where you have a ship for 2, 3, 4 months in the wind park to do the operation and maintenance, and also against a fixed offshore platform. And in the end, we saw that this kind of solution is cost competitive to the other tools in a water depth greater than 60-70 meters and round about 120 kilometers far away from shore. Whereas it needs to be highlighted that the mothership approach has a significant shortcome, and this is with regard to it's not all day available, and that is a shortcome of this approach, because if a turbine fails and you can't operate it for the next 3, 4, 5 months, then you will lose money, and that's a major shortcome of the mothership approach. If that is not the case for this approach, the mothership approach will win the game every time.
Okay, I have a few questions from the audience. One is asking, are there any design for hydrogen plant in the offshore platforms for the future? Are there?
Yes.
Yeah.
Yes, that is exactly the plan we are following at the moment. So we applied for a research project to go ahead with this idea to have an electrolyzer integrated in the platform, not in the operation maintenance platform, because it's not possible from a safety point of view. So it needs to be a separate platform with a hydrogen solution at the top side.
I see. Another question is, would this platform be able to be moved, or is it a fixed platform better for all time? No,
it is possible to move. So what you can do, you can decommission it after, let's say, 5, 6, 7 years, or the lifetime of the wind farm after 20, 25 years, and going to another site to consider the capex of the platform for more than one wind farm, to consider it for 2 or 3 wind farms. Yeah.
Right. So there's another question from Xingya from China. He asked, what would be the water depth that you're dealing with before this becomes, attractive as compared to a monopile wind turbine? For the floating wind turbine, what will be your
So we are talking about 60 meters roundabout. We will start with 60, 65 meters, because you need also a specific draft for this solution to keep it stable. If you're going with a TLP, for example. With regard to a semi-sub, it could be also applicable in 50 meters, but then the question is if a fixed platform makes more sense from a cost point of view.
Another question is, what type of naval steel will predominantly be used for this platform?
Typical shipbuilding steel. So we are working with S355 at the moment.
S355, yeah. Okay. Or another from Naji, the question is, dear Frank, many thanks for this interesting presentation. Has the design of the air gap of the topside deck structure been conducted as the offshore ONG standards, that is 100-year or 1,000-year?
Yes. So we work for the European side with a 50-year storm condition, and we worked in line with the DIN-VGL standards as well as the AIP standards. Yeah, and most of the standards were from the oil and gas, because those standards are, let's say, well done, and with a lot of background expertise from the last 35, 50 years.
Well, Frank, I got many questions, but anyway, one question is, what is the lifespan and what materials are you using to combat corrosion?
Corrosion, it's a very nice question. So in the end, we have we developed a maintenance plan to also consider corrosion protection. Sure, there is a coating on the substructure as well on the top side. For the substructure, we are also working with an active system, so then ICCP is also considered. But in the end, it's a question of maintenance. So if you're going through the platform, you need to check and maybe repaint some compartments if needed. So that is for sure. Similar to oil and gas. Yeah.
I think it use catalytic protection as well. Yeah. Anyway, Frank, because of time, there are a number of questions that you could answer while the next speaker is speaking. So I will leave you, and thank you very much for sharing your experiences and your ideas and also your discovery of your platform. Thank you so much, Frank.
Thank you.
Okay, so
thank you too. You're welcome.
So now we turn our attention to our second speaker, Professor Maurizio Colu, who is a reader or associate professor in offshore renewable energy systems at the University of Strathclyde, Glasgow, UK. So Professor Colu will be speaking on offshore multipurpose platform, especially exploiting the synergies between aquaculture and offshore renewables. So Maurizio, please.
Thank you very much, Professor Wang, and thanks a lot also to Frank. I allow myself to call him by name because we know each other since a long time. So I'm here today to present basically the results. We have not finished yet, but this is the twin project of Space at Sea. This is called the Blue Growth Farm. Those two projects were funded in the same call, by the same call of the European Union. So today I'm going to talk about aquaculture and renewables, and if we can find synergies between the two in order to develop a technically, economically viable offshore multipurpose platform. I'm Maurizio Colu, and Professor Wang has already kindly introduced me. So first of all, I would like to acknowledge the project, the European Union Horizon 2020 scheme for funding this project called the Blue Growth Farm. So I would like to spend just a few minutes on the context. So why multipurpose platforms? This is a nice slide, the nice graph from the Multiuse project. And it shows how the offshore environment that in the mind of some can appear as a lonely place. It's actually a very crowded place. There are many stakeholders, and there are even more and more by the day that are basically moving into the offshore environment for different reasons. And the question is, do we need to go alone? So each industry by itself and develop from scratch a platform, or can we find synergies whereby a platform can serve the purposes of more than one industry? So this is a nice slide. So then multipurpose platform is a term that emerged in the very last 5 years or so. So I just wanted to spend a few seconds on what we mean by multipurpose platform. So an offshore multipurpose platform for us is an offshore system designed to serve the purposes of more than one offshore industry. So as you can have seen in the previous slide, there are a number of industries that are moving from onshore to offshore, despite the harsh conditions. And why they do so? Well, to extract energy, conventionally oil, but also new renewable energy, to extract materials. You can think about deep mining, to extract food, aquaculture, but also seaweed, finfish, shellfish, nutraceutical, pharmaceutical, and so on and so forth. There are many industries that now are looking at the offshore environment. And this, by some, is starting to be defined as a new industrial agricultural revolution. So we are basically passing from extracting these resources, going around, to establishing almost, you may think of it as a city of activities offshore, where many activities take place at the same time. So it makes sense to talk together and say, can we merge our strengths and save money? So on the right-hand side, you can find a book chapter and a paper that you can download clicking on the hyperlinks. That the first one is introducing you to a multipurpose platform, and the bottom one is a review. And as Frank said, for these challenges, it's very important to consider also the other aspects, the social aspect, the environmental aspect, not only the techno-economical one. So again, this is just as an example, an artist's impression by a multipurpose platform. It's a platform where you may have, again, different industry. In here, you can see 2 wind turbines, you can see wave energy converter, you can see a maritime surveillance system. So you are out there, you can surveil what happens in the sea, from piracy to illegal transport to monitoring the traffic simply. Aquaculture, obviously, docking system. Frank talked about hydrogen. So hydrogen is also perceived as an energy vector of the future. In the future, there may be hydrogen-powered ships, so they can dock to this platform, refuel, and start again. So at the end of the day, a multipurpose platform is simply a platform that is used for more than one use. As I mentioned, I'm talking about the work that we have done and we are doing in the Blue Growth Farm, empowering aquaculture. So this is a list of all the partners, similarly to the Space at Sea project. We have people from different backgrounds, from aquaculture, from wave energy converter, wind turbines, offshore consultancy, researchers, and so on and so forth. Again, if you want to have a high-level introduction to the project, you can look at the paper on the right here, published in OMAE. So there is actually a precursor to this project. It's called H2 Ocean. It was another European project called an FP7 project, where the aim was slightly different. It was basically a platform. Sorry, it was a farm of hybrid wind and wave energy devices, as you can see on the bottom right here. So you have a vertical axis wind turbine on that use as a support platform a wave energy converter. This is by floating power plant in Denmark. And we had a farm of these that sent their energy to a central platform where we produced hydrogen. And then as an extra, we thought it would be nice to have also some aquaculture system powered by this renewable energy. Anyway, one of the conclusions of the project was that economically, one of the main revenue is not from selling hydrogen, is not from selling electricity, but is actually from the aquaculture business. So from this, the main idea about the Blue Growth Farm project. So let's not have a renewable energy farm and then add on it an aquaculture system, but it's the other way around. Let's think about an offshore aquaculture system and power it with some renewables. So the focus switched from the renewables to the aquaculture system. The full-scale concept of the Blue Growth Farm is presented in this slide. So on the left, a top view, you can see that it's a 210 meter by 160 meter, roughly speaking, external dimensions, with an internal moon pool that is more or less 160 by 110 meters. So you have a 10 megawatt wind turbine on the front part, and this is inspired by the DTU 10 megawatt design. On the front, is not, you cannot see it very clearly, but there is an array of oscillating water column wave energy converters for a total power of half a megawatt. But remember that a critical function of these wave energy converters is not only to produce energy, but is also to dampen the waves that are then occurring in the moon pool. As you may know, fish aquaculture don't like waves. They would like a flat sea. But at the same time, we need to move offshore because the near shore location for aquaculture are pretty much all taken. So there is a trend to move further offshore also aquaculture, but we need at the same time to protect them. The space, the moon pool in the middle is capable of hosting 50 by 50 meter aquaculture cages for a total production, depending on the location, depending on the fish, between 5,000 and 7,000 tons of fish per year. And then you have a docking site on the aft part. These are the other two views. So you may ask yourself, okay, this looks like a nice concept, but is it able to have a dynamic response once it's excited by wind waves and current, compatible with operational constraints of the aquaculture system, the wind turbine? An example, the nacelle of the wind turbine should not be accelerated beyond a certain amount. People working on the platform cannot be shaken too much because this can cause seasickness. The wave energy converter needs to sit at a certain relative position which is better sea surface. But also, and critically, typically we in aquaculture, we have fish grown in a cage and there is nothing around for hundreds of meters. What happens if now we put this fish in close proximity to oscillating water columns, to wind turbines? Are they disturbed by these renewables? Did they grow with the same growth rate? So basically, I'm going to focus a bit more on the 1 to 15 scale model, but in general, we developed a numerical model that is able to represent aerodynamics, hydrodynamics, structural dynamics, mooring dynamics, factors to study this platform. And in order to validate it, we developed two experimental activities. One, an indoor ocean basin activity at the Col Central de Nantes at a scale of 1 to 45, and one outdoor activity at a 1 to 15. And then there has been also an indoor experiments to double check the effect on fish growth rate. So numerical modeling, I will just touch quickly on this, is based on the classic approach of initial frequency domain analysis, where you can basically work out what are the hydrodynamic coefficients of your platform, but including already the mass of the whole platform, including the wind turbine, including the oscillating water column, and so on and so forth, followed by a time domain analysis where you are able to include all the forces acting on this platform, and you can work out, okay, what is the nacelle acceleration? Are we within the limits? What is the inclination of the platform? What is the acceleration in the cabin where the operators are? What are the internal waves in the moon pool? Are they too much for the fish grown there? So we can double check the criteria. And on the right, you can find 4 papers, conference and journal papers, where we explain a bit more how we did the dynamic analysis. The outdoor 1 to 45 prototype, as I said, was conducted in the ocean basin at the Col Central de Nantes in France. And it was thought as a first validation and tuning of our numerical model. So it was a hybrid model in the sense that we had the platform itself scaled with fruit, the moon pool, and the wind turbine. Rather than the wind turbine, we had a fan and basically with a software in the loop approach, we had an external software calculating in real time what would be the force transmitted from the rotor to the tower of the wind turbine. And this was recreated, scaled on the top of, as you can see here, of the tower, scaled model tower here, so that we can capture what is the scale model motion and therefore compare it against our numerical model. 3 configurations were tested without fish cages and with the wave energy converter not operating, then without fish cages with the wave energy converter operating, and then the full configuration with the fish cages and the wave energy converter operating. There were a lot of data collected, and on the top left, you can see some of the sea state that we have tested. And basically, we use this as a first validation, but also tuning, especially it's quite difficult, as Frank and Professor Wang knows very well, to model viscous forces on this kind of platform, especially once you have a moon pool and some sharp edges. So experimental activities are key to be able to tune these parameters. But now let's talk about the main topic. So we have to reach TRL level 5, technology readiness level 5 within the project. We said, okay, we are going to deploy a scale model in real sea conditions. So there is one partner that is the NOEL, University of Mediterranean of south of Italy. They have access to a region of the sea where they can do experiments. And we thought this is ideal for our projects. So you can see on the bottom right, a 1 to 15 scaled down model that has been installed early March and is going to be there until October, through which we are going to do experiments in real sea conditions. So we are not able to control wind, we are not able to control the waves. Everything is happening as nature says. This is a 14 by 11 meter external dimension with an open bottom internal pool of 7 by 10 meters, roughly speaking. You have a performance scaled wind turbine. What does it mean? It's for various reasons that I'm not going to explain here now because of time. But basically, you cannot scale geometrically the blades of a wind turbine. And therefore, what your aim is to make sure that the force acting on the rotor and transmitted to the rest of the platform are scaled correctly. So you're not that much interested in the shape of the blades, but more on the forces that the mass is scaled down accordingly, and also that the tower is excited, the vibration of the tower are excited in the right way. So there are a couple of articles there that explains more in details how this has been done, because there was the additional challenge of the wind speeds that are occurring in that particular site. So it was an interesting study, but Politecnico di Milano eventually made a very good design that has been installed and is working. For the wave energy converters, again, one of the main aim of this platform was to be able to validate our model. Our model is focused on verifying that all the conditions are right for this platform to operate. So externally, the wave energy converters are being scaled according to fruit and geometrically, but internally, for those of you familiar with oscillating water column, you know very well that the pneumatic behavior of the air within the chamber is key to model the power production. So internally, there is a different scaling approach in order to make sure that power production is optimized and is closer to the full-scale concept. There is a nice review of scaling law for multipurpose platform that we conducted and published in Applied Ocean Research, if you are more interested. By the way, we are aiming to have if you don't have access to those journal subscription in Zenodo, there are some of these articles freely available. This is an overview of the sensors with which is equipped the 1 to 15 scale model. So you have a huge array of sensors, to be honest with you. It was quite complicated to arrange. So first of all, on the left side, you can see the wave station, the current station, and the meteor station in order to make sure that we know what are the input metocean conditions. Because as you know, in the sea, you cannot control wind, you cannot control waves. So you need to know exactly what are the inputs, what are the wind acting on the turbine, what are the waves acting on your platform. So there is an array of sensors just to measure the meteorological conditions. Then as far as the wind turbine is concerned, as far as the platform is concerned, in the wind turbine, we have an array of sensors to measure the forces at the base of the tower transmitted to the platform, the rotational speed, the power produced by the wind turbine. The wind turbine can yaw, the pitch of the blades can pitch, and the rotational speed of the wind turbine is controlled like in a real wind turbine. We have a array of sensors measuring the motion of the platform, both at the top of the wind turbine, but also on the platform itself. There is an array of load cells and a structural health monitoring system, because another aim is to double check our structural model. And importantly, there is an array of ultrasonic probes and pressure dust transducer inside the wave energy converter chambers in order to check how they work, but also measuring the wave elevation, the water surface elevation inside the pool, because that will allow us to know how much the water moves inside the pool, so how much the fish growing in this area will be stressed, if you want. Everything is sent to the nearby shore, where there is a data center lab, where we record and post-process the data. So the outdoor prototype has been installed early March. Now we are setting up, trialing, and making sure that everything works until the end of April. And then we are planning to record data virtually continuously. A beauty of an offshore outdoor experiment is that you're not tied to the timetable of an ocean basin. Typically, an ocean basin, you can use it for a week, 2 weeks, 3 weeks, but then it costs too much to experiment for too long. Outdoor, you can leave it there for months, and we are planning to do so. So from May until decommissioning, we are thinking about around October. We plan to have at least 3 months of complete data for the platform. That will be quite nice. So watch this space, we will be publishing. So just one quick notion, as Frank said, social and the environmental aspects are very important. And at the end of the day, if this platform works perfectly, but fish are not happy to grow, we have failed. So in CEFAS, in the UK, we basically designed an experiment, a bespoke experiment, to see how much the fish grows when subject to the noise emitted by wave energy converter and wave energy wind turbines. So we started with an identification of the potential main stressors for aquaculture species. So you may be surprised to know that not all fish hear in the same way. There are some that hear high frequencies, some low frequencies, some don't hear at all the noise coming out of mechanical devices. So it's quite complicated, but I can show you this picture on the bottom, where basically we have a control group of fish that has been grown without any noise, so like in a normal aquaculture system, and one subject to the noise emitted typically by renewable energy. And you can see that there is a slight lower growth rate that needs to be taken into account, obviously, in your business model when thinking about this multi-purpose platform. So obviously I had to compress a lot of things in just 20 minutes, but I put papers there. There are links here where you can find plenty of more information, and I will be more than happy to answer your question. Finishing up with this nice picture in the middle here. What you can see in the background is the famous Mount Etna in Sicily. So the platform is in the channel between Calabria and Sicily, Messina Strait, and I found it very nice. Thank you very much.
Thank you very much, Maurizio, for a very awesome presentation. I enjoyed so much. Always listening to you, I learned something. And especially that the fish doesn't grow that well with a bit of noise. That's interesting. Now, there are a number of questions here. So I will just take a few and ask you these questions. Have you or how have you quantified the operational limits for fish well-being with respect to piston sloshing in the moon pool? If so, can you elaborate on this? And what are limits when fish well-being starts to be negatively affected? Do you have this problem with sloshing in your moon pool?
Yeah, as people from oil and gas know very well, whenever you have an internal moon pool, there is a complicated hydrodynamics taking place with internal waves, external waves partially transmitted. So there has been one of our colleagues in this project has just published a paper on this particular topic. So basically, and excuse me if I don't use the right jargon, but basically fish continuously swim in aquaculture cages, and they do so normally. But so when there is a bit of currents or a bit of motion of the water due to the waves, that's okay. They can cope with it. And actually, they can develop a more muscular tissue that is good for selling. Anyway, when this speed becomes excessive for a prolonged amount of time, so the fish can occasionally speed up and swim a bit faster, and not a problem. But if this is continuously happening, they become fatigued, and this become a problem from a growth point of view. So basically, they measure the speed of fish in fish length per second. So how many of their own length can swim in 1 second? And there is a limit there. So basically, the reason why we have wave probes inside the moon pool, together with marine currents measurements, is to make sure that the speed within the volume where the fish are growing does not exceed for too long these limits, in order to ensure that the fish are happy inside those cages, basically. Thanks. But I'll be happy to share with you that article.
Yeah. Another question, Maurizio, is you use a 1:15 model. How do you come about this size? And is there any future larger model scales that you're going to look at?
Okay, from someone like me that develop numerical models, the ideal would be to have the 1-to-1 platform, because there are no scaling issues, perfect forces, I can model everything. Obviously, this from an economical point of view is not possible, especially at the early phases. So the 1:15 is a compromise between being closest to the 1-to-1 scale, but at the same time being economically feasible within the budget of the project. So this is a 10 million euro project with a lot of partners for 3 and more years. So at the end of the day, we had just a limited amount of money to spend on the prototype. And this is the biggest model we can come up with, economically speaking. So we were uncertain between 1-to-10 and 1-to-20. Eventually, we managed to do a 1-to-15. And that was also a limit imposed by the wind turbine itself. So it was quite difficult to have some minimal forces with a smaller turbine than that one. So there were a lot of compromises, but eventually this was a trade-off between cost and the closest to 1-to-1, basically. The plan is, once this project finished, we have a work package dedicated to the business model. So the plan is to present these to some different stakeholders in aquaculture world. As you may know, in Norway, there has been already installed a huge farm offshore of hexagonal shape. And there are other projects for ship-shaped farms far offshore for fish. So we want to see what is the interest in this platform, and the next step, the next natural step, again, will not be the full-scale concept, but maybe a demo of larger scale, maybe 1 to 3, 1 to 5, where you have all the system operating like in a real platform.
Another question, Maurizio, is how much power normally aquaculture require for the operation? And are the current technology of wave energy converters, can they provide such a power?
That's a very interesting question. It is one that caught me by surprise. If you take the typical aquaculture farm size, I'm talking about salmon farms here in Scotland, for example, they do not need a lot of power compared to the power that is produced in this platform. So you may have 100, 200, 300 kilowatt of power needed per farm. And this is mostly used to blow the feed from the feeding barge to the cages. So you may ask yourself why you have 10.5 megawatt on the platform. Well, the plan is also to export some of the energy back offshore. So if you think about wave energy converter, I think that they can reach the level to power a farm, an aquaculture farm. Obviously, it's of paramount importance, the storage system, so batteries or other systems to store the energy, because obviously renewables don't give you a nice constant source of energy, but it's alternating. So you need to make sure that you have a clear idea of what is the power demand from aquaculture that varies during the day and varies during the seasons and vary with the growth cycle of the fish, in order to make sure that at any given time you're able to provide the power required.
Yeah. Maurizio, there's also a question on what kind of CFD software you use to carry out your numerical simulations. Do you write your own code or you use a commercial software package?
For the, we are actually used a number of packages because we have done some internal code-to-code comparison. So the model that we have seen, and the main one where everything is represented, is the package by DNV CESAM. So where we go with Jenny designing the platform to Hydro D Wadam to perform the frequency analysis, the domain frequency analysis. Then we have SIMA Reflex for the time domain analysis and PostRep for the post-processing. But also there are our friends in Reggio Calabria used Aqua to double check some of the hydrodynamic aspects. And the people in Politecnico di Milano used OpenFast, especially Aerodyne, as to double check the characteristic of the wind turbine. And they are developing their own OpenFast version of this. So this is the software that we are using.
Yep. You know, Maurizio, there's so many questions here, 16 questions, but anyway, we ran out of time. But you can have a look at the questions, and it's quite interesting. Some of the questions are quite difficult also to answer within the prescribed time that we have left with. So I think we can stop here. But
there is my email address there, so if you want to email me those questions, I'm be happy to answer.
Yes. Also, I would like to thank you again, Maurizio, for a very, very nice presentation and also very sharp answers to some of the questions that have been raised. So to the attendees, today you have heard about the multi-purpose platform and co-location of aquaculture and wind farms from our two eminent speakers. So if you have further queries, please do contact the presenters or me, and we'll try to respond to you. Also, thank you for attending today's webinar, and I look forward to seeing you again in future Blue Economy CRC webinars, which will be announced in due course. So I want to wish you a very great evening or a very great morning, depending on where you are. Thank you. So signing off now, CM.